Okay. Let's say with our three rubber bands, they're in equilibrium, and this one's 8.4 centimeters long at a 37-degree angle with the positive x-axis. Okay. And I'm going to measure all my angles from the positive x-axis because it's very convenient to do that. Okay. And this one's 12.2 centimeters long at 143 degrees. Okay. And this one's 16 centimeters long at 270 degrees. So we'll call this vector call this vector B, and call this vector C. We also have this picture. We're going to assume that all the rubber bands have the same force characteristics. So that if the length of the rubber band, I call that L, length of the rubber band is L. I don't usually like a lowercase l because if I type it, it looks like a 1, and it gets real confusing. Okay, usually use an uppercase L. But since I can write script, it's beautiful, don't you think? Okay, yeah. I'm gonna write another one that good. Okay, anyhow, there it is. Okay, I'll use this script L, but if I was to type this, I'd use this capital L. Okay, and up here, force. Okay, and okay, we'll do the force. So my force function is going to look something like this. And you know what I ought to do? I ought to make this graph a little steeper. Not using up. We make better estimates. The same characteristics, but a little steeper. Okay. Okay, so the force is not linear. Okay. The force increases quickly, then the rubber band stretches out, and some miracle occurs in the polymer chains that kind of rub against each other. And it gets a little easier to stretch, but then you get it out too close to its maximum length, working length, and it starts to resist you more. Okay, that's what that graph tells you. Think about that. Okay, so there it is. And let's just put units on this. Let's say this is 10 newtons. And let's just say the length here is 12 centimeters. Well, actually, because of the numbers I use, I should probably call it 16. Okay. So there's 16 centimeters. Okay. So how long is the rubber band when it starts exerting a force? Okay. Okay. So we got a good estimate. Somebody said that ought to be about 6. This is in centimeters. And you know, if we do this and find the midpoint 8, it'll be about here. 6 makes perfectly good sense. Okay. And I don't know, I found the midpoint there. Let's see there. And they're pretty good. Not great. Okay. Okay. So my question is, what are your own estimate? How much force is this exerting? How much force is this exerting? And how much force is this exerting? Sketch your own graph. Don't be meticulous about it. Just sketch a graph that kind of looks like that. Okay. You know, concave down, then it's kind of inflection point goes concave up a little bit, right? Go ahead and sketch the graph and estimate what forces these things are exerting. Let me just point out, there's the graph, okay? Here, I'll make another one. Not exactly the same. That's okay. Maybe I'll put 16 here. And maybe I'll put 12. Okay. A couple reasonable numbers. And then this might still be 6. In this case, it might be 5. Probably 6. And then I want 8.4 centimeters. So I would estimate where 8 is, and then I'd maybe say, okay, here's L equals 8.4 centimeters. And then I draw a projection line over here. And I say this would be going to call this the force that's exerted by this rubber band, F1. Going to call this force F2, question mark. I'm going to call this force F3. Question mark, we haven't estimated it yet, okay? So let's say 8.4 centimeters is going to give me F1. So I'm going to say, okay, F1 equals, well, there's 12. So half of that would be 6. Let's say 4.5 newtons at 37 degrees. F2 equals what? I got to go up to 12.2. Well, there's 8, there's 16, so here's 12. There's 8. I put those things down. I project up here, I come across here. I say, oh, that's about 5.5. At 143 degrees. F3 equals, well, it's 16.7 centimeters. Seven newtons at 270 degrees. Okay. Now, what's the result of those three forces? If everything has been measured accurately, it should be pretty close to 0. I don't think it is. It should be, okay? Because I just made up numbers and made up a curve, okay? In my second curve, my first curve would have given me better estimates, but that's okay. Your curve, yeah, my curve gets a little flatter than this one ever gets, and yours might too. Or maybe yours never gets quite that flat, but it still has the right characteristic. Okay. If you hang weights from that rubber band and measure its length for each rubber band, you're going to get something like this. Not pretending the same curve goes for all 3 rubber bands. You've got 3 identical rubber bands. That's not going to happen in the real world. So you'd have to measure all 3. You'd have 3 graphs and make the estimate for each one. Does that make sense? So it's straightforward. Okay. So how are you going to calculate the result? Well, a couple of ways you can represent this. So I'm going to say, F1x about 3.6 newtons, and F1y is about 2.4 newtons. Okay. If I've got the numbers right. 37 degrees is kind of a nice angle to use because the cosine is about 0.8 and the sine is 0.6. Very close. Okay, so you can use that to at least 2 significant figures and it'll be okay. So you don't have to necessarily go to your calculator to do it. It's real easy to punch that into your calculator. Okay, and you want to write it out to reinforce until it's automatic to you how you get these components. Okay, maybe it is already. Then should be putting arrows over these to keep scaling. F2X is 12.2 centimeters. It's 5.5 newtons. Cosine of 143 degrees. Cosine of 143 degrees automatically gives you the negative sign that you know you have to have for the x component because it's going this way. Okay, and that's going to be 3.3 newtons. That's okay. That's all right. F2y equals 5.5 newtons sine 143 degrees, and that's going to be very close to 4. There's something wrong with one of my calculations. I'm still on, but 2.7 newtons. Okay, then F3x equals 0 because it's at 270 degrees. You can write it out, 7 newtons times the cosine of 270 degrees. But the cosine of 273 degrees is 0, so you kind of skip that. But if you don't want to skip it, it's fine to write it. F3y would then be negative 7 newtons. You can do that by inspection, or you can do that by multiplying by the sine of 270 degrees, which is negative 1. Multiply the magnitude times the sine. Okay, well, there are several ways we can sum these. The sum of your forces is do I and J. I just want to do that. Okay, so here's force 1. Here's force 2. Here's force 3. Makes sense to group these by like terms. 3.6 newtons times I plus 3.3 newtons times I. Something's wrong. One of these has to be negative. This is negative. Minus 3.3 newtons times I plus 2.7 newtons times J plus 4.4 newtons times J. This actually does work out pretty well. Minus 7 newtons times J. So here are I components. Here are J components. You just add them up. We get 0.3 newtons times I. And then we get 2.7 and 4.4, 7.1 if I count right. So that's one newton times J. So that came out a lot closer than I expected it to. Okay. Now, do you understand what I did? All this is automatic if you know the trigonometry. You don't necessarily have to write it out this way. You could write out like this and write the x components, 3.6 newtons, negative 3.3 newtons, 0 newtons, and add them up, and you get 0.3 newtons. The y components are 2.7 newtons, 4.4 newtons, and negative 7 newtons. And just by luck, all these come out really close. I didn't think they were going to come up nearly that close. Now, this would be a good result for the lab. Okay? Be a good result. If you come out that close to the three vectors, adding up. Okay. And there are other ways to picture the vectors. You just got to know how to work with vectors. Okay. Now, it would be nice if we had a formula for these, because then we could program it, get all kinds of good results, and maybe we put these rubber bands at different angles and different configurations, and you want to do a spreadsheet. Okay. And if we're going to use a formula for this thing, simplest formula is a linear formula. Okay. Now, it's not linear, it's not a straight line. But if we sketch a straight line that basically comes as close to the points of this curve as possible on the average, if I had that colored chalk that I want, my chalk go. Okay, I'll use green. Okay, so let's say I can just kind of sketch a line like this. If that line doesn't deviate from the curve by a whole lot, right? And that's going to have a formula y equals mx plus b, right? And if that's 10, it looks like m is maybe negative 2.6. It looks like the slope, well, from this point to this point, the run is 10, which is very convenient. We've got a run of 10 and we've got a rise this big. If 10's that big, it looks like what's 0.65 L minus 2.6. That's for this one, okay? And you can do all these things not by estimates, but calculations. Now, if I did it for this one, you know, the line, that's not the best place the line could have been, but that looks like, and it's not Y, it's F. It looks like F equals, okay, that looks like about -1 there, maybe -1.5. And from, let's say from this point to this point, my rise is this. And my run is this, the run is 10. The rise is this, which looks like maybe 5. So it would be 0.5 L minus 1. Okay. So if I want the force at 8.4 centimeters, well, 0.5 times 8.4 is 4.2. That would give me 3.2 newtons. Okay. Not all that close to my estimate, because of course my curve was above graph at the point when I made that estimate. Plus, I didn't make a very careful estimate. Okay, I just did a ballpark estimate and showed the procedure. Okay, if I use this, that's about 2/3, and 2/3 of 8.4 is, come on now, 1/3 of 8.4 is 28. Okay, so it's 56, 5.6 minus 2.6. Okay, so if L is 8.4 centimeters, I get about 3 newtons here. What did I get here? I got 3.2 newtons, okay? Not a huge difference between these models, but if you go out far enough, there is. Now, the only point I'm making here is these linear models work pretty well, okay? And they're a lot simpler to work with than the model that works for this. What kind of polynomial would have a graph that looks like that? Remember any pre-calculus? Third degree, exactly. Okay, cubic polynomial has, you know, can have one inflection point, it can have 2 relative maximums. It doesn't, but if you turn it around a little bit, it has real maximum, relative minimum. So that's good. That's good. You remember some pre-calculus. You probably did that in your calculus class too when you analyze these things. Okay. Now the problem with a cubic polynomial is if I want to know how long the thing needs to be to get a given force, I've got to solve a cubic equation. And it's not a nice cubic equation where you can find roots easily. Okay. So kind of stuff is graphical procedures or something analogous to graphical procedures. If you can get a reasonable linear model, it can still give you a good idea. But times you just got to bite the bullet and go with your cubic model. Okay. Okay. Well, there's a little bit about analyzing data, about making estimates, about making sketches, to get the idea, to get the picture, instead of just going to software and putting a bunch of numbers in it and pressing a button and hoping it's right. It doesn't take long to do this ballpark sketch analysis. So when you press that button and get the answer, and it tells you that the resultant force is 7,000 newtons, aimed right at you, okay, you know that something went wrong instead of reporting that to your supervisor, which would get you in big trouble, I think. It just, you know, it's got to make sense. You can figure out what makes sense pretty quickly. You do ballpark back of the envelope calculations pretty quickly. Okay. You can use these linear models and get something pretty quickly, crunch a few numbers. Okay. If you want to take it a little further, before you go doing the fancy stuff that you can't do by hand. Okay. So the idea is you got to understand approximations and how they work, because everything's an approximation when you're engineering. I'm sure I'm overstating that, so any engineer that listens to this, don't bother writing me, I know better. But you know better than I do, okay? If you're an engineer. To the extent to which what I just said. So, okay. But pretty much, all the tables you use for the characteristics of materials, that's not worked out theoretically. It's worked out in a lab with certain pluses and minuses, okay? And so forth. Conductivity of a circuit, okay? You know, they're measured pretty accurately. You pretty much take that stuff and rely on it. But remember, it's all approximation as soon as you get outside of physics. And we do a lot of approximations in physics to make sense of what we're seeing. It might be a little sloppy. Your lab is limited. Analyze the forces you have from your picture and paper, okay? Based on your force measurements that you took when you suspended the weights. And make a graph of it, just like we did here. Okay, now, you know, I took a ramp in the ball. Ramp was supported just as it was in lab by a domino on its side, 60-centimeter ramp. And I haven't gotten the work from everybody, but I saw some work that gave me a pretty good suggestion that the acceleration of that ramp is around 15 centimeters per second. Now, Audacity will give you times easily down to 3 decimal places, down to the thousandth of a second. And the 10,000th of a second is relatively okay if you have a sharp sound. Okay, you don't always have to sound. So when you use Audacity, especially when we're trying to compare to see if the acceleration is uniform, and you just use one significant, one decimal place on something that takes 2 seconds, well, what's your percent uncertainty there? It's plus or minus 0.1 out of 2, that's a 5% uncertainty. And you're going to use that to calculate accelerations, that's going to get you up to 10%. And then if all your numbers are within 10%, then it's plausible that we have uniform acceleration. Okay? But it's not very definitive. If we use everything to 3 significant figures, and after you've written out one equation and solved it, you just say, okay, use Excel to do the rest of these. You just set up a spreadsheet to do those calculations. There you go. You don't have to write out the details of every one. Although at this point, I kind of want you to do that just for reinforcement. But ultimately, you're going to be able to show me how you solved one equation, how you used it to find whatever it is you're looking for. Okay? And then say, these are calculated similarly. Here's a table. Here are my accelerations. At 10 centimeters, it was 17.1 centimeters per second squared. At 15 centimeters, it was 14.8 centimeters per second squared, et cetera. Okay? So, but I saw a cluster, not a whole lot of deviation. There's also uncertainty in the way you read Audacity, and the more you zoom in, the more accurate you're going to be, and the less leeway you have in making bad estimates. Okay? If you're off by 1/10 of a second, boy, that's serious in this case. Okay? That gets you up to maybe close to 20% error on some of the results. Okay, and you want to think about that. Anyhow, enough digression. Okay, so I say 15 centimeters per second squared. We start the thing at rest and we roll it all the way down the ramp. Okay, how fast is it going to be going at the end? And that's very easy. You can list your kinematic variables. I'll use VF instead of just V. There are times when you want to use VF when you're looking at a specific interval where you do have an initial and a final value. There's sometimes you want to use V, as we did in class last time. We were talking about a function that applies to a bunch of different questions, okay? And there are appropriate uses of both. So what do we know? Well, we know this. We accept tentatively the one reasonable measurement we got for acceleration when we started zero. So what equation has this? Okay. And what are we trying to solve for? VF. Okay. We can use this equation because we know x minus x naught, we know v naught, and we know a. And v naught is 0, so this becomes 0, so we can easily find time. But I don't think that's what I asked for. I think I asked for the final velocity. Okay, maybe I asked for the time. Okay, so this would be a valid calculation if you want to know how long it took to get down there, and I might have asked that. So you're going to get something like 490 centimeters per second squared if you're going to do this in centimeters, and 60 centimeters here. So you're going to divide 60 by 490, which gives you something pretty close to 1/8, like 0.125. Wait a minute, something screwed up. Give me just a second to stare at this. Okay, yeah. I didn't get enough sleep last night. I was using the acceleration of gravity here. I wasn't thinking. Okay, acceleration, we told you, was 15 centimeters per second squared. You divide that into 60 centimeters, and you get 4 seconds squared. And you take the square of that, you get 2 seconds. Okay. I think it takes more than 2 seconds, so I don't know about that result. That's one. So closer to 3 seconds for me, but like I say, working on short sleep, maybe I don't know what a second is anymore. Okay. So anyhow, you can solve this. You can get T. Okay. And then you can get VF. You just multiply your acceleration by that T, and you get about 30 centimeters per second. Okay. Now, directly, you could have used okay, this is going to be 0. That's easy to calculate. 2 times A is 30 centimeters per second squared. Okay, not 1960. Okay, times your 60 centimeters. That's going to be about 1,800 centimeters squared per second squared. And the square root of that is about 42, 43. Centimeters per second. Okay, so yeah, what I wanted you to do, what I asked you to do was identify these and tell me what equation you're going to use to find VF. If you use this equation, then maybe I didn't ask you for VF, maybe I asked you for T. Okay. And you could use that to find VF, but you want to find VF directly, you got an equation that'll do it for you. All right. Yeah, no, you should know that. You should have solved, several problems. Maybe 20 problems that use these things and cause you to have to reason it out. And if you haven't done that, you just don't know it well enough to use it efficiently and get chapter 3 homework done efficiently and understand what chapter 3 is telling you. So, you got to do these things. Okay. Then what I'm going to do is I'm going to draw a picture and I'm going to say, that this line is horizontal. This length is 60 centimeters. And this height here is 2 centimeters. Okay. So question is, what happens after the ball goes off the edge and falls to the floor? We'll say 1 meter below. The question is, how far did it go? Well, for the projectile, V naught is now your, we'll say 40 centimeters per second. Okay, so I'll say it's approximately 40 centimeters per second. It doesn't make sense. Another haywire calculation. Well, okay, now that's what I get. Okay, it's not consistent with what I get here in the given acceleration, so you can fix it. But that's how you do it. 20, 42. Yeah, okay, well, I estimated 43. And I was thinking about 42, but I didn't want to show you. Okay. So I allowed myself to be a little careless. We're going to round it off to 40 just because it's an easier number to work with. Okay, V naught is 40 centimeters per second. Okay. What is V0x and V01? Harder to stop. Okay, so anyhow, what I asked originally, and I'm sure I was quoting it to just repeat it. What I asked for was tell me the 3 variables you know. Okay. And then tell me what equation you're going to use to find the final velocity. Or maybe I asked for the time, okay? If you're gonna find the time, use this equation. If you're gonna find the velocity, you're gonna use this equation. And it should be obvious to you why, because each of these equations contains the quantity you're looking for and three known quantities, okay? In this case, you'd be solving for t, this, this, and this. This is 0, that makes it easy. You don't have to go to the quadratic formula or heaven forbid, try to factor the thing. It's not going to happen. Okay? Okay, well now we figure ballpark final velocity is 40 centimeters per second. So what do we have? We have the ball coming down here. We know that we can let that ball go off the end of the ramp and fall to the floor. So we want to know how far it should go. Right? Okay, well, then we have X motion and we have Y motion. So we better know our initial velocity in each direction. Make sense? Okay. Now, there's one way to do it. You got enough information here to figure out this angle here, which is going to be same as this angle, which could give you this circular angle if you want to use it. I mostly use the circular angle because it's easier to see the angle than if I try to draw a little tiny angle in here. Okay, I'm probably going to use that little tiny angle and understand that the y velocity is going to be negative. Okay, so what's the thing? I automatically go to arc tangent. Should have been the arc sine. I mean, you look at this triangle, the sine of this angle is this over this. So this is the arc sine. And you can plug that into your calculator. Okay. It's got to be 1/30th of a radian, 60 centimeters. Didn't write that very well. So that's approximately 2 degrees because a radian is approximately 60 degrees. Okay. A 30th of a radian is 2 degrees, and it's a small angle, so that approximation works just fine. Well, you don't really want to do that, even though you love to work with degrees. We can directly figure out what the sine and cosine are. So we don't need this. Over here and say, sine of theta is -2/60, which is -1/30. We didn't have to take the arc sine of 1/30 to find that. And we don't have to use 2 degrees. You don't have to find the sine of 2 degrees. Okay, now you got your calculator, you can find the sine of 2 degrees, pretty close to 1/30. Okay, 0.033, maybe 0.3, maybe even 5. But there it is. Okay, what's the cosine of theta? That's a square root of 899 over 900, which is approximately, make sure I get enough nines in here, 0.99 thousand minus 1. 0.995. Maybe another 9 in there. As I said, I didn't get enough sleep. I don't want to think that hard. Okay, got that? So you can calculate it. It's easy to reason out. Well, with the approximations we made and the uncertainties in our measurements, we might as well call this 1. Okay. Now, a couple of principles that you really want to make note of and use. Okay, Sine of theta is approximately equal to tangent of theta is approximately equal to theta. What are the units of theta? Okay, so we got this. Okay, well, negative 1/30th. 1/30th is your angle in radians. 1/30th of a radian. Theta is measured in radians. If it's measured in radians, then if theta is small, sine of theta and the tangent theta are both close to theta. Okay, this is 1/30th of a radian. You think you take your radius, which would be 60 centimeters, in an arc of 2 out here, it's 1/30th of a radian. Okay, that's how I got something close to 2 degrees. You want to try thinking in terms of that. Makes it a lot easier to visualize and see things and make numerical estimates. It give you quicker ideas than doing a bunch of calculations where you lose track of what anything means. And they're very commonly used in physics, especially, but I think in engineering too. Engineers can correct me on that. Once you know enough, write me a letter and say, nah, okay, or yeah, sorry. Okay. Anyhow, we got this. Cosine theta is close to 1, and it's confirmed. This angle is about 1/30th of a radian, because if you do your arc of a circle, you got about 2 centimeters on the arc with a radius of 60 centimeters. It's 1/30th of a radian. If you don't understand that, review radians. You really need it. And you're really going to need it second semester when you start doing calculus with sines and tangents and worse things. Okay. Learn to think in radians. You're going to need it when we start really analyzing the rotating beam. Okay. And the cosine theta has got to be close to 1 because the sine of theta is small. Sine squared of theta is really small. So 1 minus the sine squared of theta is really close to 1. And the square root of 1 is 1. Don't understand that? I just part reason about yourself. Here's a numerical example. Okay. I do think there's probably another 9 in there, but I don't think that hard. Okay. Bottom line then, V0x is cosine theta is real close to 1. 0.9995. Okay. Twice as close to 1 as 0.9999. Better write that extra 9 in there, I'm pretty sure. I don't quite trust my mental picture. Okay, do you know what? Using theta measured from the positive x-axis, we're going to get a negative. Okay. So I'm kind of slopping over that, but it's about negative 1.3 centimeters per second. Sine's 1/30th. It's negative 1/30th. Negative 1/30th of that is negative 1.3 centimeters per second. Well, the question now is, how far does it go? What can you do to figure out how far it goes? Okay, now I got some good answers to my questions. My question was, how are you going to figure out how far it goes? Well, I immediately got the answer. Well, figure out how long it takes to fall. Multiply that by the x velocity, right? Because the x velocity ain't going to change. Formally, the x acceleration is 0, and the y acceleration is downward acceleration of gravity. Okay, so here we have this. I'll make this steeper than it really is. Here's your V naught. So there's your V0x, there's your V0y, just the horizontal and vertical components of this vector. So we know okay. Now for the horizontal motion, we know V0x and AX, but that's only two things. We don't know the X minus X naught because that's what we're trying to find. Okay. We don't know final X velocity. We don't know how fast it's going when it falls. We'll tell you it's about 4.2 meters per second. Kind of seen something similar to that. We don't know how long it takes to fall. Okay. So we're stuck. We can't directly find from these two pieces of information how far it goes. We need time. If we have time, we can do it. Fortunately, vertical motion and of course, it's not X minus X naught anymore. It's Y minus Y naught. Really bad A. Can you tell that's an error? You strain yourself a little. I don't want to have to rewrite it. Vertical motion, we know V naught Y, A Y. It looks like that. Maybe you can't even. Okay, A. Both. On T. T applies to both the horizontal motion and the vertical motion. Then we can use T because it's common to both. Time flows the same for the vertical as for the horizontal. That's it. That's an easy question. Okay. So once you work that out, should be no problem. Work it out, send it to me just so I can sleep better. Okay. And really, I mean, y'all are affecting my sleep. Can't figure out what it is. Well, okay, so here we have this. Now there's another problem, which is much, much harder that you want to maybe think about. Okay. We have a ball that falls that goes down the ramp. And it's this. And we know this for the projectile motion, right? This X minus X naught. And we know Y minus Y naught. And we know, let's see if we gave you that or not. Okay, well, one thing is we know theta, so we want to find V naught. Okay. Now, another variation of this is we know the magnitude of V naught, we don't know theta. Now, both of these problems are somewhat harder than this one. So think about it. What do we know about the y motion? We know something about v and y. Let's say it's negative v naught sine theta, right? And for x motions, we know v naught cosine theta. V naught x is v naught cosine theta. What else do we know about y? Ay equals negative g. You choose your units. Okay. Y minus y naught is known. We know ax and we know x minus x naught. Well, we can write down an equation of motion for x and an equation of motion for y, but we have that theta. We have a sine theta on this side and cosine theta on this side. It complicates life a little bit because we can't solve this t because we don't know theta. Okay. We can't find v naught x because we don't know theta. So what do? Well, you might want to start pondering that a little bit. Kind of tricky. Okay. I had trouble with it when I took the course. So you're probably going to have trouble with it. Some of you maybe not. Got to keep your wits about you and think about what you know and figure out what to do with it. Okay. But that's kind of a hard problem. But we need it for lab. We need to solve it. We just need to see the solution. Might not see it until we do another lab, but that would give us another measurement of how fast the ball is going at the end of the ramp. If we can determine how far it goes down here. Okay. And we know this angle, which we can easily find. I didn't know my stuff was going to get famous like that. I'll cut the